All right, we left off with this. This is page 3, where we were talking about acids and bases and looking at a new definition. So we left this one question. Why do we call H plus a proton? So let's just review why do we say that? It's an H plus, a hydrogen ion. But we also call it a proton. Why is that? Let's just review if we have our symbol, for example, our isotope symbol. We have our element, right? And it's number 1. So it has 1 proton in the nucleus, right? And its mass is 1. So how many neutrons does it have? It has 1 proton and 1 electron to be neutral, right? 0 neutrons. If it loses the electron, then it's just a proton by itself. We call it a proton, and that is what distinguishes Bronstead-Lowry acid from its conjugate base, or the Bronstead-Lowry base from its conjugate acid. So we're defining the acid as the one that gives the proton. It gets rid of it, it pushes it away. So that's like the great tennis player who just every time you hit the ball, he sends it back. The base is the one that accepts the ball, right? So that's the one that accepts the proton. It ends up with an extra proton after the transfer. So we defined our conjugate acid base through that transfer of the proton. So here we're going to take one of these and move it here. That gets us to conjugate acid base pairs. And it's important to identify when we have those pairs together in solution. And they differ by just 1 proton. So we identified our Bronstead-Lowry acid and base, and I'm going to say those are the reactants from the way the reaction is written. Then we'll identify the conjugates as products. So let's do that for these examples. So which one is the Bronstead-Lowry acid? Here we have sulfuric acid, so hopefully you recognize that as one of our strong acids. It's got that one-way arrow. And then what must be the base? It must be the water. Because if we connect these two, they differ by just 1. So this HSO4 minus hydrogen sulfate ion is the conjugate. Is it an acid or a base? If we compare these two compounds, H2SO4 has an extra H, HSO4 minus has lost one. So that is going to be the conjugate base of H2SO4. If we say that the water is now our base, and it's connected to the H3O+, they differ by just 1 proton, so those are conjugates. Then H3O+ is what, an acid or a base? It's definitely an acid. It has the extra proton. And that's actually what we define as acid when we calculate the pH. So this is the conjugate acid of water. So there's a relationship there where they differ by just 1 proton. Now let's do the same thing for part B.
Excuse me, I have a question.
Okay.
So if water adds hydrogen, it turns into acid.
Mm-hmm. Yes.
Okay.
So in part A, water is the base and hydronium ion is its conjugate acid.
It's like such a big difference between water and acid only because of 1 hydrogen.
Yes. Yes, exactly. Okay, and in the next one, let's put the reactants first. Which one is acting as an acid? We can look at where that transfer happened. Which one gave up the proton? Water. And that means that the dihydrogen phosphate ion accepted the proton, so it will be the base. Now, when we identify the conjugates, H3PO4 is conjugate acid or base? That one has more protons. So it is the conjugate acid of dihydrogen phosphate ion. So they differ by just one proton. The one that has extra protons, more protons, is the acid. And that is phosphoric acid. So maybe that's familiar. It is a weak acid, and that's why we have this two-way arrow. All right, what about OH? Is it an acid or base? That is going to be the base of water. So notice that water can go either way. Water is neutral. It's right in the middle. So depending on what it's reacting with, it can act as an acid or it can act as a base. So that's called amphoteric or sometimes amphoprotic. So we're going to use this idea of transferring a proton, and then we're going to use the idea of strong and weak for the arrow type to write the reaction for each of these things in water. So we need our list of strong or not for the arrow, and we need our Bronstead-Lowry definition to transfer the proton. Transfer the H plus. This section is probably one of the hardest parts of the acid-base area, is predicting these reactions in water. So what is nitric acid? That is HNO3. All acids are aqueous. We'll go ahead and put it in water, and now we want to complete that reaction. Which one is going to donate the proton? Which one is going to accept the proton? So we'll identify the acid. Is it strong or weak? That's right. This is the strong acid, so that will give up the proton. So we're going to form H3O plus NO3 minus. And it's strong, so it all goes to products, 100%, one-way arrow to products. Now what about bromide ion? We'll go ahead and put it in water. There's only one way to transfer the proton. So let's write our products with that proton transfer. Do you recognize anything that helps you write the correct arrow?
I think the bromic acid is strong acid, so then it's going to be one way.
In which way? Yeah, as soon as that hydrobromic acid forms, it gets rid of the proton. It does not keep the proton. So maybe water tries to offer the proton, but no, HBr is strong, it sends it right back. So this one, we would say there's no reaction.
And Professor, how do we know which way the arrow is going?
Well, because a strong acid always has an arrow that's 100%. So for example, when we talked about HCl, this goes 100% to H plus Cl minus. So it's a one-way arrow. HBr works the same way, but if it's a product, it's going to push back to the reactants. So what we see is when bromine is by itself in water, it is neutral. It just floats around. There's no reaction. All right, let's take a look at acetate ion. There is our acetate ion. Let's put it in some water. Now remember, the hydrogens by the carbon are not acidic. So there's only one way that this proton can transfer, and that's from water to the acetate. What do we recognize here? Well, let's look for the acid. Do you see an acid that's familiar?
Yeah, it's a weak acid. It's acetic acid. So it's going to be a two-way reaction.
this is our weak acid. We recognize the acid because of the COOH, that carboxylic acid group, but it's not on our list of strong acids, and so it must be weak. And that means we're going to have everything at the same time. Everything will be there at the same time. So we have a two-way arrow because it's weak. So that shows us the difference between a weak acid and a strong acid. If it's a weak acid, everything will be there at the same time. If it's a strong acid, you saw in the previous one it was no reaction. We're not going to form a strong acid. That will always just prevent that from happening. All right, let's look at hypochlorous acid. Now on our list we had perchloric, so this one is weak.
In the previous example, when the acid got a hydrogen, why wouldn't you just write CH4 COO?
Oh,
Or
yeah.
not even COO, but CO2.
You can write it, but when you do that, usually you'll see this written as H in front, CH2H3O2. So we have seen it this way, and they're showing that one of those hydrogens is acidic, but these ones here, these three, they're not acidic. So let me draw that. Let me show you why. We have CH3CO. This is what the structure looks like. And so for these guys here, those are not acidic. They're not coming off. Carbon is going to keep the hydrogen. It's not going to share them or let them go. So these ones are not acidic protons, darn it. However, this one is acidic. It can come off because of those oxygens. So that COOH group, the COOH, is called a carboxylic acid. And that carboxylic acid group is common in a lot of different molecules in biology, such as, all of your amino acids, and citric acid has 3 of those groups. So it's very common. It's our usual weak acid group. It's a carboxylic. And I show the structure with those COO because it looks funny, right? It looks different. And that's because they are connected to the same carbon. And because of that structure, it allows the hydrogen to leave easily. So that's what makes it acidic, and that's why we show it in a different place on the formula. Let's get back to hypochlorous, which is weak. That's going to have a two-way arrow, and hypochlorous is an acid, so we're going to give that proton to the water. Oh, I have 2 different things written there. So write that down, a little typo. What are we going to do? Let's do the nitrite ion. And that is NO2 minus. Sometimes the acids are easier than the ions, and that's why I'm doing the ion. Maybe it's a little bit trickier. Let's put it in water. We could transfer the proton to form nitrous acid, which is weak. And then that's going to leave the conjugate base of water. And so we'll get a two-way arrow from that weak acid.
How you determine which one is going to give up the proton?
Well, if we just look at the reactant side, for the NO2 and the water, there's only one way to transfer a proton. But maybe in D, is your question about D? There we have to recognize that that hypochlorous acid is the acid. So basically, anytime you have water as a reactant, it is going to do whatever the other reactant wants. It goes both ways. So if you put it with a base, the water is going to act as an acid, and if you put it with an acid, the water is going to act as a base. So it can go both ways depending on what it's combined with. So let's take a look at pH. pH means the power of hydrogen. We're going to use pH because it helps us take something that has a huge range of value from something small like this would be 0.1 all the way up to something that's tiny, right, like 10 to the minus 14. It is so small. And these are measured in terms of molarities, which is moles per liter. So I'm now realizing why I like to do chapter 10 first, but the content is so much more mathematical and challenging that I like to bring this in first. So we do have to be counting our concentration correctly using moles per liter when we see those square brackets. But we're basically talking about moles of H plus or H3O plus in every case. So let me complete that, moles of H plus. Now that gets a capital M. That is so small. 10 to the minus 14 is so small that normally we would call that 0, right? This is one of those things where if you owed me 10 to the minus $14, I would say it's okay, just keep it, right? It's so close to 0. We would normally call that 0 a long time ago, right? But not with acids and bases. With the number of particles, Avogadro's number of particles, that amount of H plus has a really important consequence. Okay, so we're going to take that huge range from 1 or 0.1 all the way down to 10 to the minus 14, and we're going to take the log of that so that we get the exponent. We can talk about the exponents just in terms of like 0 to 14. That's much easier to keep track of for humans. So we will need these formulas, and here's how we go backwards. If we need to find out how much H plus is in solution, we're going to reverse that. We're going to take 10 to the minus pH. Another thing that we'll consider in our calculations is that for a strong acid, and let's just look at that question again, HCl, the reaction, it never stays together as a neutral molecule. 100% breaks apart. When you start with, say, 1 molar of hydrochloric acid, which is pretty strong, you will have that same amount of H plus. So in that case, we're saying that the amount of HCl that we start with, all of it goes to the H plus. And those are the kinds of calculations we're going to look at in this class. Now, if you have a weak acid, and so we're thinking about something, remember HF was an example of a weak acid. We have a two-way arrow, so we have H plus F minus. And for every 10,000 of these, we have just one each of these. And so what that means is we cannot calculate the pH directly for a weak acid. So we will not calculate pHs for weak acids at all. We will only calculate the pH for a strong acid. Let's take a look at the pH scale. At the low end, we have acids that those turn the litmus paper or vegetable dyes, they turn them red. And when we have a low pH, because of that minus sign, we have a lot of H plus. At the high end of the scale, we have basic solution, and that will turn our vegetable dyes blue. When we have that, we have a very small H plus concentration. One thing we kind of skip over here, and it is given, it is show up right here. So I'll go ahead and show you what happens with the water. Remember how the water can go both ways? Well, it will always split apart to keep the amount of H plus and OH constant. And so that's what this is indicating here. 10 to the minus 14 equals that H plus times the OH minus. So there's always both present in solution. This is for water, and I'll just go ahead and show the whole thing. we're going to make one H3O plus, which is equal to the H plus. Right? It's only different by that water molecule, and it's there. It's just we didn't write it. Plus OH minus. So we've shown that transfer from one water molecule to another. One water molecule acting as an acid, one water molecule acting as the base, and those concentrations will always be present. There will always be some present in any aqueous solution. So the question is, if they're equal, we're right here, neutral. If you have extra OHs, if you have more OH, then it will be basic. They're all present in solution, but here we're saying on this end, the H plus is greater than the OH minus. And on this side, we're saying that the OH minus is greater than the H plus. But because there's water, we will always have both. Anytime there's water, we will have both H plus and OH minus. It's just a matter of, are they balanced in the middle? Are they neutral? Or is there a lot more H plus or a lot more hydroxide? Let's go ahead and look at the pH. We're going to use these equations to go from our H plus concentration to the pH, and then we'll use that scale to decide if it is acidic, basic, or neutral. Okay, so when you do this, you'll type it into your calculator. It depends on what kind of calculator you have. So make sure that you're using your calculator and getting the right number. And we'll go ahead and use extra digits. We're not going to worry about the sig fig rules for these calculations, but just use some extra digits. All right, 6.5. So that is about right here. And maybe it's weakly acidic. It's just barely on the acidic side. It's pretty close to neutral. Okay, so let's do that for these compounds.
Sorry, where did you get 6.5?
From this equation here, I did pH equals minus log of 3.0 times 10 to the minus 7. So check your calculator and make sure that you are pushing the buttons and know how to get these numbers correctly.
Just explain with number one, just very briefly, but simply, what do you put into your calculator? All I see is 3 times 10 negative 7, exponent. How do you get 6 out of it?
On my calculator, I have to type the log button first. Some of them you type the number and then press log. But on this one, I have a Casio. I type the log button, and then that gives me this. And then I type 3, you can do EXP, or mine says times 10 to the, right? So these are buttons. And then I do the negative button, and then 7. Right, and then I'm going to do equals, and I end up with minus 6.5228. And then I have to remember this negative sign here. So the pH is 6.5228. Don't round it too soon. Okay, because we're not going to worry about the significant figures, but we don't want to get rid of them. We want to keep the information. All right, both of these are, are these acidic, basic, or neutral? Yeah, these are both on the acidic side. Yeah. What about this last one? What do we do with this? This equals our H plus concentration. So then we can still do the same thing. The pH is minus log of that value. And that one is 1.90. So very acidic. Nitric acid is a strong acid. We could get a pH of 1 from different solutions, and that would be strongly acidic but it's not necessarily all nitric acid. We could get acidic compounds from other acids as well. I want to talk a little bit about buffers, and then we're going to switch over to the chapter 14 worksheets to talk about these two-way arrows. So we're going to talk a little more about that type of reaction, and then we're going to come back to buffers. And then our next lab, we'll see the colors and take a look at this behavior. So we're really kind of doing the preparation for your lab. All right, so a buffer solution is defined. It has two important things to know. One is the definition. It's a weak acid in solution with its own weak conjugate base. So it's got to have that conjugate acid and the conjugate base together in solution in order to be a buffer. Now, the important thing about a buffer is that it resists the changes in pH when small amounts of strong acid or base are added. So why is this important? Let's think for a minute about our blood. We know that there's a carbonate buffer in the blood. Life forms are incredibly sensitive to changes. We really need to have a very consistent homeostasis in order to maintain life. And so if you drink a soda, which has a pH of 2, we drink a very acidic, maybe lemonade. Lemonade's probably not a pH 2. Something very acidic, but your blood needs to maintain like 7.4. How does that happen? How can you drink a soda and yet that acid doesn't change the pH of your blood? It's a very important issue, and the way that happens is because the blood contains a buffer. It has two buffer systems at least. So that resisting the change in pH is very important for physiology. So let's take a look at some of these examples. Oh, this has a typo on it. This is one example. This is supposed to have a carbon in there. Acetic acid is a weak acid, so if it's together with acetate, then that would be a buffer system. Here we have a weak base, right? Ammonia is a weak base, and we have its own conjugate acid. So that can serve as a buffer too. And then here's another one. This one is the carbonic acid with hydrogen carbonate. So they differ by just one proton. So they make a buffer system. Now what if I had carbonic acid together with carbonate ion? Would that make a buffer? No. Because it's not a conjugate acid base pair. They differ by 2 protons, so it's not going to make a good buffer. Notice that in this graph we show one line with pure water and we're adding HCl, and that pH goes down really fast. But when we have a buffer and we add HCl to it, it holds it pretty constant, right? It's nearly flat. And only after we've added a lot more HCl, right? So it's only resisting pH for small amounts. But when you have a small amount, it's very constant, and then it starts to trail down a little bit more over here. We could have HCO3 minus with CO3 2 minus. That differs by just 1 proton, so it's a conjugate acid-base pair. All right, so I want to come back to this when we do the lab, because these questions are just like your lab questions for the acid-base lab. And so I'm going to come back to these. Our next section is going to be in chapter 14. So if you can read chapter 14, that'll probably help.